right up here. First thing that I want you to know. First thing that I want you to know is that first thing when you walk in tomorrow, you will be doing some data analysis with the data that you just took. Okay? So I'm going to find averages for you. I'm going to give you a data set, and I'm going to ask you to do some analysis with that set, okay, about free fall motion. So I'll give you some graph paper. I'll ask you a question. I'll have you do some calculations. It'll be great, okay? It's going to be like an AP Physics test problem that you will do with the data that you took, all right? So just be aware that that is coming up tomorrow, okay? Right now, we are going to start moving from free fall into two-dimensional motion. So we're going to start that, though, by actually looking at what free fall motion looks like. We have not really spent any time doing what are called motion maps, but today is going to be the day. So I would like you to have paper out right now because we're going to write down some things, and I need you to draw a picture for me. Okay, so here we go. We're going to talk about dropping an object. So when we drop an object, first of all, if I drop that object, if I let it go, it's going to start off at a velocity of 0. And as it falls, tell me about its speed. It will increase, right? It will increase in the negative direction. And if it increases in the negative direction, what's going to happen to the distance over each set of consecutive seconds? So like if I release the ball here, and then after 1 second it's here, where is it going to be after the next second? Further down, right? The distance is going to be greater. And after the next second, it's going to be even further down. So it's going to be like this, and then over there, we're going to go like that. So that's the first thing that I want you to recognize and to know is that the distance is going to get bigger and bigger and bigger. And I think you kind of know that, but I just want to really articulate that. So that's the first piece of a motion map. The second piece of a motion map is that you can use arrows, vectors, arrows to describe the velocity of the object, okay? So at the very beginning, we're going to have a velocity of 0. And then as it falls, its velocity is going to increase in the negative direction. So I'm going to put a little arrow. I'm going to even make it a little bit smaller because it's just starting its motion. And then go ahead on your paper and draw the arrows for the subsequent times, okay? Once you've done that, then check with your neighbor, see if they agree with you. Have just a really quick conversation about what that looks like. So Abhishek, did you guys agree back there? Did you guys talk or no? Have you talked yet? You guys are still talking? Have you talked yet, ish? Okay, talk right now. Take a moment. I'm trying to rush us through because I want to make sure that we have time to get into the fun part here.
You can't beat the best. Family talk.
All right. Now you've had time to talk? Yeah? So Abhishek, can you tell me what your team said in terms of what happens to those arrows from here to here to here to there? They get bigger and bigger each time, right? Does that make sense to everybody? Okay. That should not surprise us. Hopefully that's what your team said, is that the arrows are going to get longer and longer each time. So the blue arrows that I have represent the velocity. If I was going to draw another set of arrows, so I'm going to use a different color. If you're writing in color and you'd like to do that too, you are welcome to. Otherwise, if you just want to make them maybe dotted arrows, would you draw for me vectors that represent the acceleration on the ball at every given point? Could you do that for me? What is the acceleration going to look like? So I got a ball out so you can watch it, right? So it's just after I released it, and then at subsequent seconds after that. What is the acceleration going to look like? If you would like to talk to your table mates, that would be a fantastic thing to do.
All right, guys, it's going to increase until Let's keep it up.
They have to be
Let's keep it up. I'm right. We're all right. It's good. This is our right here. You got it.
You got an answer?
Yeah, go ahead.
Okay. I'm gonna make sure everybody else. Are we okay? You ready to talk? Yeah. And are you volunteering?
I volunteer.
Okay. What did you say? What do your acceleration arrows look like? If there are any, I should ask that. If there are any.
Will increase. Acceleration will increase.
They will increase. So how much acceleration does it have at the beginning?
0. Wait, yes, it has some. I don't know.
No. That's why we're doing this, right? If you all knew all the answers to all the questions I asked, then what would be the point of being here? So you're going to say it has some acceleration at the beginning. Can you guys see the difference in those colors? Maybe I'll draw them over here. The acceleration here, you said it has some. And why do you think it's going to increase? Are you getting, yes, you are. You're getting closer to the Earth. But if we look at the radius of the Earth relative to how high I'm holding that ball, like this is not drawn to scale, but here's the Earth, and here is me releasing the ball, right? Like, whoa, we can't even do it because it's so darn close. It's like right there. Like literally not even, that is not even drawn to scale. Are you with me there? Okay. That's like Mount Everest, right? Like, do you understand what I'm saying here? Is it really getting that much closer appreciably? No. Should the acceleration vector change in each of these cases?
Yes.
Niam, you're like vehemently shaking your head. What is the acceleration if it has a value up here? The acceleration as I release this ball. Negative 9.81, right? And as it's falling, tell me about the acceleration. It's the same darn thing. Are you with me there? Now, my little smart friends over here are going to say, but we're getting closer. But I want to make a point, friends. We can do the math, and I would love for you to come in and we can actually do the math and figure it out. It is so minuscule, the change.
But it is increasing.
But not enough that you would actually be able to document it given this arrow. Does that make sense?
Yes.
And so for our purposes, is the acceleration changing?
No.
It is not. It is 9.8 the entire darn time. So I want to make sure, oops, I was going to make these all the same color, that your arrow is exactly the same every single time. So I'm going to take this guy, I'm going to put him right over here. Okay, and then I could do the same thing every single time. It's going to be the same size every single time. The acceleration, I'm going to make a note here, and I would encourage you to do that as well. The acceleration does not change. We don't think, or we're not including any air resistance, okay? And as we do that, the acceleration does not change as that ball falls. So far, so good. Okay. Yes or no? I didn't actually get a yes.
Yes.
Yeah? Okay. Next question for you. What if I take my ball, and we're going to assume that this is a super flat surface. Harris, I'm going to have you catch this because I'm not going to go run after it. I want you to watch this ball as it rolls. We're going to assume no friction. Here it comes.
Can I stop here?
Good job. All right. So as it rolls, we're going to watch that go just like a buggy as it's going. Thank you so much. Okay. As that's going, I'm going to just draw this one right over here along the floor. So here's the floor. So I've got another ball, and it's rolling. And as it rolls, so this is after I've given it the push. Okay. I am no longer in contact with the ball. It is rolling, and so after the first second, it's gone this far, and after the second, how does the distance compare? They're the same, right? It's the same distance apart each time. Would you please, on that picture, would you please draw velocity vectors, velocity arrows that show the velocity of this ball as it's traveling? Again, this is after I've given it the push, so it's already rolling. How do those arrows compare to one another, ladies and gentlemen? Same? Same? And in what direction are they going? This way? To the right? It's like they're listening to some sort of music. They're all the same. Okay, that's our velocity vectors. Then would you talk to your table mates and draw the acceleration vectors, please? We're assuming that it's well, so I'm ignoring my push. Are you with me here, Isaac?
Yeah.
I'm ignoring my push and I'm ignoring Harrison's push. All I'm doing is that middle bit. That middle bit. What do the acceleration vectors look like? Ian, did you guys have a conversation about that? What do the acceleration vectors look like? What's that? Why not? The acceleration, say that again.
There's no acceleration.
Okay. So the velocity in this case is constant. So, Henry, you were right. There is kind of it's not really a trick question. It's just a are you paying attention question. Their acceleration vectors all equal 0 because there is no change in the velocity. Okay. So that's a nice quick review of what we did already in physics. There you go. That was your review for first trimester. Here we go. We've got 4 minutes, and Rizan, I need you. Come on up here. All right. So I've got a couple of ball bearings. You should take a look at them. Okay. Now, I didn't ask this question for you or to you. Would these arrows change if I change the mass of the ball bearing? Any of them? No. So good question. I mean, fair question though, right? None of them. None of them will change because mass doesn't matter, right? Mass doesn't affect velocity, doesn't affect the acceleration. It does not matter. So I'm saying that even though those two little ball bearings are pretty much the same, right? Would you agree? Is there anything different about those two ball bearings? That one has a hole in it, and it doesn't. Okay, so there are two. I know, right? It's kind of interesting. And the reason I have that, you're gonna be my human ring stand. Are you excited? Come on over here. Just gonna be my human ring stand. It's a very exciting job. So I got this fancy little device right here, okay, that I can pull back like this, okay? And the one with the hole in it, can you hear me, that one? Okay, the one with the hole in it, I can stick like that. Whoop, whoop. And then when I click this little thing, it kind of falls off. Do you see how it fell? Yeah, I kind of get a little kick. I'm surprised by that. It should just fall straight down. Let's try that again. So let's see if we can just get it to fall straight down. That kind of launches. That's surprising because it didn't do that before. Anyway, so it launches a little bit, but it goes pretty straightforward. The reason it's supposed to go straight down, I'm just kind of surprised by that, is that when I do that, the other side, because this is like just a little bar that goes across here. You see that? There's a little bar. So when I pull this back, the bar goes that way, okay, to give me a place to put this one. But then watch what happens on this side when I flip it. It goes that way. Does that make sense? And so it does that so that I've got this other ball bearing that I can put here, and then it can get a kick. It can get a real kick that way, okay? So Razan's going to help me with this in just a minute, but before I do that, I want you to think about this. I want you to think about, we'll call this one the one that's going to go straight down or pretty much straight down. I'm going to call that one ball A, okay? And then the one that's over here, the one that's going to get the kick that's going to go this way, and Harrison's going to go have to chase that ball in a minute, but we're going to call that one ball B.
Gilbert.
And my question for you is, I want you to write this down. You don't need to discuss it. I just want you to have a commitment on your paper. Which one is going to hit the ground first? Is it going to be ball A, the one that goes straight down, or the ball B, the one that goes out this way? That's my question for you, okay? You need to write down a commitment very quickly, but write it down on your paper. I think it's going to be ball A. I think it's going to be ball B. Again, ball A is going to fall more or less straight down. Ball B is going to go that way. All right. I need to stand right here. You have glasses on, that's why I called on you because, safety and all that.
Am I safe?
Yeah. Well, move back just a little bit. You'll be all right. You have to hold that really still. All right, you guys, you gotta listen up because we gotta do this fast. I want you to listen because you have to listen. Otherwise, you can't tell. Where's your office? You're a brave girl.
Damn it.
I heard.
One more time?
I think.
One more time. Let's
so.
listen one more time. Gotta make sure it's oh!
Change my answer.
Tomorrow we'll do it. All right. I'll see you tomorrow. Bye. Nice job.